And with that, I would like Ventu to start his presentation, the first one for today.
Thank you, Gerald. Just to confirm, can you see my screen and hear me?
Yes, we can.
Okay, thank you. Well, thank you for that introduction, and thank everyone for attending. We understand and know that your time is valuable. It's really the only commodity you have to offer. And so we appreciate you spending some time with us today. I'm going to talk about a case history of a bidirectional test that was performed on a drilled shaft in sand, gravel, and cobble deposits. The presentation is based on a technical paper which was presented at DFI's annual meeting last fall in Chicago. I'd like to recognize the paper's co-author, Marco Fallon of Tetra Tech in Tetra Tech's Missoula, Montana office. We'll go through three major sections, if you will, of the presentation. We'll present some background, some details on the project and the drilled shaft and the test. Then we'll look at the test results themselves and what the testing showed in those types of deposits. And then, true to the theme of DFI's It's Money initiative, we'll look at the benefits of that testing on the design and construction, focusing as much as we can on cost and money. And we'll also highlight some maybe non-quantifiable benefits as well. Those three major benefits being the use of a higher resistance factor due to the testing, the presumptive values that might come out of this testing that were demonstrated in these deposits, and then one that's not as often thought of, but the benefits of the testing that were applied during the production shaft's construction. So this is a project that's going to replace a bridge over the Clark Fork River in Missoula, Montana. The picture on the right is of the existing bridge. The new bridge will be actually two 3-span bridges. They'll construct a new one next to this existing bridge, and then when that bridge becomes in service or comes in service, they'll demolish this bridge and construct the second one. The project consists of a total of 26 drilled shafts for support of those two bridges. There'll be 8 shafts in the river, 4 for each bridge. Each of those shafts will be 71 inches in diameter and 65 feet below mudline. And then there's also 8 abutment shafts, varying in diameter from 48 to 54 inches and varying in embedded length below ground of between 30 and 35 feet. So right from the beginning of this project, as designed, it was intended to construct a pre-construction shaft, if you will, although the shaft was the first abutment shaft, production abutment shaft to be constructed, and a bidirectional static load test to be performed on that shaft. That was known in the project specifications, and that'll come into play in the choice of a resistance factor. And so at one of the abutment locations, one of the abutment shaft locations, a river pier sized shaft was constructed. That is, its diameter and base elevation were the same as a river pier. Subsurface conditions are represented in the figure on the right. We'll discuss them just kind of in general. There was about 12 feet of fill. It was silty gravel. You can see the blow count there, the corrected for overburden end value of 30 and the phi angle of 32 degrees. These end values and phi angles were used in software to predict the nominal resistances of the shafts through these deposits. Below that was a fairly consistent deposit, although here on this schematic it's divided into 2 substrata. The upper one, again, both of these consisted pretty much of gravel with silt sand and cobbles and occasional boulders, which, as we know, can be somewhat difficult to predict unit shaft and base resistances in these types of deposits. The upper deposit, again, kind of lumped together and characterized with a corrected end value of 40 and a design phi of 34 degrees, whereas the lower portion of the deposit below the jack assembly had a slightly higher corrected blow count and a slightly higher phi angle used in design. We can see here that the locations of the 3 strain gauge levels in the shaft. We'll talk a little bit more about those later. Above the jack assembly, and the 2 strain gauge levels below the jack assembly. And we can see the shaft segments as they're divided up and designated, where the individual shaft resistances were calculated from the test results. So kind of a mental picture, if you will, of some of the results we'll see later, that where the strain gauges were located and how the shaft segments were designated and broken up. These are the deposits that came out of the shaft spoil virtually full depth. So this gives you a sense, you know, sub-rounded to sub-angular, not real angular, and the gradation and the broad range of particle sizes, again, right from some silt right up through cobbles and boulders, pretty consistent throughout the depth of excavation of the shaft. So this test shaft on land, although it was to emulate a river pier, had a diameter of 5.9 feet and an embedded length of 75.5. As we said, using those end values and internal angles of friction, the phi angles illustrated on the previous schematic, resistances, both shaft and base, were estimated using the software Shaft 6.0, and we will compare how those presumptive values based on those end values and phi angles compared with measured results later in the presentation. Because it was known right from the start that a bidirectional test would be performed, the production shafts were designed using a resistance factor of 0.7 applied to both shaft and base resistances as calculated by the software Shaft 6.0. The bidirectional jack assembly consisted of an upper plate and a lower plate and 3 embedded jacks, each having a capacity of 2,200 kips. So since they act both upward and downward at the same time, that gives us a potential total test load or maximum test load of 1,320 kips. As we saw, the instrumentation included strain gauges both above and below the jack assembly. Here, this is a picture of a typical strain gauge installation. The strain gauge is in the green rebar. It's a number 4 rebar, 36 inches long, with a vibrating wire strain gauge at its midpoint, mounted on the reinforcing cage. And so again, 5 total levels of strain gauges. Temporary casing was installed, full depth. It was installed with an oscillator and removed during concrete placement. Here we see the jack assembly being lowered into the shaft just as it's about to clear the top of the casing, which extended above grade. The as concreted shape, that is after the concrete was placed, was determined from thermal wire profiling, and this is a representation of the diameter of the shaft as determined by that thermal wire profiling. We can see the reinforcing cage depicted here. One of the benefits of thermal wire profiling as opposed to CSL tubes is that the thermal wire looks outside the cage. And we can see here at near about 55 to 60 feet was where the jack assembly was. We can see an apparent necking of the shaft, although since thermal wire is based on temperature, that jack assembly creates a heat sink. And this is a common signature in the thermal wire profile where the jack assembly is, that the temperatures decrease and we see an apparent necking. I say it's apparent because, again, it's caused by the heat sink of the jack assembly at that location. Just as an aside, the bidirectional static load test was performed 20 days after installation. I come from a driven pile background, always concerned about time-dependent capacity gain or loss. So it's common to report the setup time, if you will, or the standoff time between installation and testing. The jack assembly was sized such that it would have extra or additional capacity from what was anticipated. And the load increments were selected such that even at a low failure load, if you will, or low capacity evidenced, we would get 20 or more load increments. And as it turns out, the guess was very low on the mobilized resistance that would be evidenced during the test. And so we ended up with 54 load increments, each of 200 kips, and each held for 10 minutes. Lots of load increments, but very well defined results, and if those results were plotted, very well defined curves. The picture on the right shows the general setup. You can see the instrumentation where the jack is, the pump, the readout box for the data logger and such is under the tent, and the test pile is shown where the rebar is sticking up there on the left. A little closer picture of the test setup itself. The engineer there is operating the pump to pressurize the jack assembly. There's two digital levels shown there on the right. Those measure head displacement as the head moves upward and out of the ground. All the electronic instrumentation was read using a data logger system. There's only 5 parameters that are measured during a static load test, and all others are either calculated from those measured ones or at least have a calculated component to them. So direct measurement during the test included hydraulic pressure to the jacks in the jack assembly, which then gets converted to a force based on those jacks calibration relationships. A head displacement is measured directly, again, using the digital levels and targets on rebar extensions above grade. Upper foundation elastic compression, that's upper foundation is between the jack assembly and the ground surface. Elastic compression is measured directly using telltales of that elastic or that foundation portion. Jack assembly expansion, that is the amount that the plates move apart or the jack opens up during the test, is directly measured using displacement transducers across those bearing plates. And foundation strain at each of the strain gauge levels is measured by those strain gauges that we saw a picture of earlier. So those are the 5 parameters that are measured from a bidirectional test. Everything else has a calculated component to it. Picture on the right here, we can see the metal tubes that look like, metal tubes are vibrating wire displacement transducers on top of telltale assemblies. So the maximum test load that was applied was 10,700 kips, and the upper portion of the test pile failed by coming up out of the ground. It reached its geotechnical resistance, its nominal geotechnical resistance, before the lower portion did. And we'll see that in some of the results and the way they're presented. So let's transition now to the results and common results and the way they're commonly presented. This is what we internally in the office refer to as a butterfly plot because it looks like a couple of butterfly wings. Vertical axis is the jack assembly bearing plates displacement, and the horizontal axis is the test load. So the red line is the upper plate upward displacement. The blue line is the lower plate downward displacement. You can see the test loads are not equal for both upward and downward direction. The upward test load is decreased by subtracting the buoyant weight of the upper foundation portion from the jack assembly force. But you can see that the upper portion here is trending toward asymptotically vertical, so that the upper foundation portion is evidencing geotechnical failure, whereas the lower portion is still fairly linearly taking load. The strain data are converted from strain measurements to internal forces. This is an internal force profile. The vertical axis is elevation. You can see the strain gauge levels are identified. And the horizontal axis is the compression force within the pile. And so at the jack assembly where the force is applied, the internal force decreases upward and decreases downward thanks to shaft resistance. And the decrease between any two strain gauge levels divided by the shaft surface area between those two strain gauge levels yields an average unit shaft resistance for that segment. And so that is how the unit shaft resistances are calculated. This is half of the loading increments are shown just for clarity. It gets really busy if we plotted all 54 load increments. Excuse me. But this is the basis for the unit shaft resistance determinations, the TZ/QZ plots, which we'll talk about, and ultimately the equivalent top load curve. So jumping into some of those results on the left here, we see what's commonly referred to as TZ curves. The vertical axis is the average segment shaft resistance, unit shaft resistance, versus the displacement of that shaft segment relative to the surrounding soil. The unit shaft resistances are calculated as just described, differences between the internal forces divided by the surface area between those locations. And the segmental displacement is calculated by summing strains that are measured within the foundation. And again, this is usually referred to as a TZ plot. On the left, we see the TZ relationships for the strain gauge segment, or for the segments above the jack assembly, and on the right are the TZ relationships for the shaft segments below the jack assembly. Again, just without a lot of detailed interpretation, just trying to give a sense of the way the data is collected, used, and evaluated. We also look at base displacement, or I should say base resistance versus base displacement. The plot on the, and these are often referred to as QZ plots. The plot on the left here, the vertical axis on the left is total base resistance. The vertical axis on the right is unit base resistance versus base displacement in the horizontal axis. Again, these are referred to as QZ plots. And these data, these plots, the TZ QZ plots, are plugged into a program called TZ Pile, and equivalent top loading response of the pile is estimated. In other words, the shaft, base, and total displacements versus load of the shaft or test pile, had it been top loaded in a static test, are estimated. So this is what the unit shaft resistances come from, or are based on then, for comparison to those predicted by the predictive program ahead of time. So it's this equivalent top loading curve on the right that forms the basis for the values, unit shaft and base, to come out of the test. So based on this equivalent top loading determination, then the shaft resistance was estimated using a method called the L2 method, as well as the FHWA 5% failure criteria given in the FHWA design manual. So based on that look and comparing that to what was predicted by shaft 6.0 using the N values and internal angle of friction values determined from the subsurface boring, in terms of shaft resistance, that program predicted 2.5 KSF. What came out of the test was actually 5.1 KSF. In terms of base resistance, unit base resistance, the program that predicted about 41 KSF, what came out of the test was actually about 77 KSF. And recall that the base resistance was not fully mobilized. The 77 KSF is what was mobilized or evidenced, not necessarily ultimate. So again, just looking at these numbers in broad terms, the test results indicated values on the order of twice what the predictive values were from the program run. So the construction proceeded, the design was fixed based on presumptive values. And so the lengths were slightly modified, and we'll see that later. But design proceeded, construction proceeded, and CSL testing was called for in all of the shafts. Now, at the time this paper was finalized, the manuscript went final, 4 river shafts had been constructed and had received CSL testing. So within those 4 tested shafts, the CSL testing indicated varying degrees of anomalies at the base of 3 of the shafts. And the shafts had been designed with base resistance contributing to their capacity. But since these anomalies were discovered, the shaft's resistances were revisited using the higher values determined from the testing program, and it was decided that those shafts could support the design loads without any contribution from base resistance. And so that was another way in which these results were applied to the production results, that the contribution from base resistance was no longer necessary given the high shaft resistances that were indicated from the testing. So that's a background of the project, the testing, the results, and a little bit of the production aspects of the application of those results. So let's define, if you will, more definitively call out what then the design and construction benefits of the testing were. Well, the most obvious and direct and immediate was that if you do testing, you can generally use a higher resistance factor. If you're working in ASD, allowable stress design, that would translate into a lower safety factor. So for this particular project designed under FHWA guidelines, as we mentioned earlier, a resistance factor of 0.7 was applied to both shaft and base, as opposed to 0.55 for the shaft and 0.5 for the base that would have been required without any testing. So the application of that higher resistance factor saved 16 feet of length per river shaft, which doesn't sound like a lot, but they are in the river and there's only 8 shafts. So after subtracting all of the testing costs, that includes contractors' costs, testing agency, engineering, that's a net savings of $25,000. So the testing paid for itself plus a little more. And again, that doesn't sound like a lot, but there aren't a lot of shafts on this project and there isn't a lot of length involved. It did also save 4 days of construction schedule. The higher resistance factor did. Hard to put a cost on that. There's no dollar associated with that, but we all know how important schedule is and that time is money, especially for a project like this where a bridge needs to be open or traffic is impacted. The shafts could have been made shorter given the test results if the only loads to be resisted were compression, but actually the length of the shafts were now controlled, design was controlled by lateral resistance requirements. So again, depending on the project, depending on the load requirements, the load resistance requirements, further length could have been saved, but in this case, it was lateral resistance that ended up controlling. A more subtle benefit, potentially long-term and future, is that perhaps higher presumptive values for unit shaft resistances and unit base resistances could be used now going forward. We saw that the results indicated twice, on the order of twice the value that was used originally in the predictive software. And so either in the private sector or the Montana DOT can use these higher presumptive values for designs going forward. This is especially beneficial for an agency like the Montana DOT, who's a repeat user. It's not as though this is the only project they're going to build using drilled shafts and this is a one-time result that they get to apply only on this project. So again, hopefully this paper and publishing these numbers gets out there into the community and less conservative designs result going forward. Maybe the biggest benefit and the one that's the hardest to quantify and often overlooked is the benefit that these results had when it came to addressing construction, call it issues or things that arose during constructions. I mean, we mentioned that anomalies were indicated by the CSL testing in 3 of the 4 shafts. Since the paper was written, there was 1 other shaft that indicated anomalies at the base. So a total of 4 shafts may have had to have been cored. If the Montana DOT determined that those anomalies were suspect enough, they may have initiated a coring program. And after that coring program, maybe if the core results were again suspicious enough, maybe require base grouting. You know, a large effort in both time and expense The easiest one of those to quantify was the time, and so that's all that's been offered here. But with only 3 shafts potentially to be grouted, the contractor estimated 3 to 4 weeks. Maybe with 4 shafts to be cored and grouted, that might jump up to 4 to 5 weeks. So again, this was precluded by the values demonstrated by the testing program, showing that the shafts had enough resistance and shaft resistance only. And so this exploration, coring, and potential grouting was taken off the table, and that was a great benefit for this particular project. So that kind of concludes in a nutshell the aspects of the benefits of testing on this particular project. We'd like to recognize the owner, the prime contractor, the drilling subcontractor, structural engineer, and the geotechnical engineer of record for the project. As I mentioned, the case history, or this presentation, was based on a case history paper. And so if you're interested in more details, a more elaborate or complete presentation of the case history, you're encouraged to go to the web page there shown, GRL's home web page, under the reference papers, and the complete paper is available there. So that concludes the presentation. Again, thank you for your attention. I will be happy to answer questions now if it's felt we have time. Otherwise, I'll be available at the end, as Gerald says, when we have a time allotted for general questions for all the speakers. So thank you.
Thank you, Van, for a very informative presentation that shows that testing does save money. Sometimes money that you cannot necessarily express in dollar terms, but you illustrated those parts very well.